A major tool that we're going to need in order to find the distributive law for cross product is something called the triple product formula. Now, the triple product formula comes from finding the volume of a parallelepiped in two different ways. Let's find it in one way first. What I want is just the area of the base times the height. Now notice that C is not the height. What we want to do is think of this as a big slanty stack of cards, and we're just going to push the cards over, and we'll find the volume that way. It should just be the area of the base times the height. Now, how am I going to get that straight up height? Well, I need something that goes straight up like this. Well, what goes straight up like that is A cross B. So this is A cross B like that. So what we want in terms of the volume, and we're going to calculate this twice. First one real seriously and the second one not so much, is the area of the base. Well, what's the area of the base? The area of the base is the area of that parallelogram, and by definition, that's the length of the cross product. Now, how am I supposed to find the height? Well, what we're going to do to find the height is project C onto A cross B. And so now we're going to have to use the projection formula. Remember, this is a scalar, it's a length, and so we're going to multiply this length times the length of the projection of C onto this. And we have a nice formula for that. That's just going to be C. Remember, this is times, not dot. This is dot, right? This is A cross B. And remember, the projection formula has A over the length of A cross B, just like that. So what happens? Well, you can see that the icky stuff all crosses out. We're going to get C dot A cross B, and dot product is commutative, so we can rewrite this so it feels better. We can write this as A cross B dot C. Now that's not the triple product formula, that's half the triple product formula. All we did at the moment was to calculate the volume where the parallelogram formed by A and B was the bottom and C was the thing sticking out. But what we can do, and we'll just try to translate this whole picture, is turn it sideways like this. And now what we can see is that B cross C is the bottom and A is sticking out. And all we want to do is translate that whole picture. So what we should get is something like B cross C dot A. So it's going to be B cross C dot A. All right. Just by turning the picture around and recalculating the volume with a new bottom, we should get something like B cross C dot A. And again, dot product is commutative, so I can rewrite this as A dot B cross C. So now we've calculated the same volume twice. And the first time, where A cross B formed the bottom, where A and B formed the bottom, sorry, and the second one, where B and C form the bottom parallelogram, but they're the same volume, so those two things have to be equal. I'm not sure who thought of this first. You're talking about really bright people, probably in the late 1700s, or maybe 1600s, 1700s I'm thinking. Anyways, the formula that we want is just that A cross B dot C is the same as A dot B cross C. So here's the triple product formula. It's A dot B cross C is exactly the same as A cross B dot C. In other words, if you try to associate these parentheses with these parentheses, the cross turns into a dot, the dot turns into a cross. In either case, by the way, if you think of this, this looks like length times width times height no matter how you do it. So it feels like volume, it looks like volume, and you actually have these really cool properties of dot product interacting with the properties of cross product. Pretty cool, and we're going to use it in just a second.